Sorry for getting a little bit of a late start here today. I've been running behind all day, um, but I think we're okay. I think we're all set. So, yeah, we're good to go. Let me get this out of the way as well. There. Okay. It's been a long time since we saw a slide deck. So, you know, hopefully this will be fun. But it's not going to be as fun as past ones have. I'm sorry. I just didn't have time to do a lot of code and animation within, but that's okay. So today we're going to be talking about persistent storage, and also along with persistent storage comes the ideas of how your application handles data and the flow of data through it. If you've been starting to work on your final project, which I hope you have, you will probably have been finding that making everything in your project, in your app, a state variable on a view that is then passed in via bindings, or whatever to subviews, is a little bit clunky. It starts to get really big really fast. We're going to be looking at how to kind of clean that up and make that a little bit nicer later on. As a part of kind of beginning to have that discussion, though, we're going to talk a little bit about persistence. Persistence is a specific term that gets used to mean saving your data. It's fancy programmer speak stuff. We like to make things more complicated than they are and call them things that people who don't program don't recognize, because that's just the kind of people we are. So, persistence. First, let's talk about the layers of an application. So we haven't talked a lot about this because we haven't talked a lot about application architecture so far. Primarily, we've been learning about Swift, the language, general programming concepts in Swift, and UIKit and SwiftUI, two of Swift's frameworks. We're going to be starting to talk for the rest of the class about architecture and how to construct your application from a kind of metacognitive high-level view, okay? So when you're thinking about the things that go into an app that is on a phone, there are different quote-unquote layers of code. These layers are defined as the kind of distance from the deepest part of the device, aka like bytecode, right? The stuff that's running directly on the CPU, and the stuff that's interacting directly with the users on the screen, right? It's a way of modeling and thinking about all of your different types, your structs and your classes and your views and your models and all that stuff. So, in terms of layers, if you go and you look up, programming application, gotta fix this to my ear better. If you go and look up programming application layers, you'll find diagrams that have like 5 or 6 layers, maybe 8, 7, sometimes 4. The ones that are 4 are pretty old, actually, from the 90s, 2000s. I prefer to break it down into 3. If you get asked about layers of an application in an interview, refer to not me, okay? I just like to simplify it, all right? So in terms of layers of an application, there's basically 3 things that you, as an app developer, kind of have to worry about. You have to worry about the presentation layer. The presentation layer is the things that you show to the user. So this is your views, or your view controllers and your UI views, if you're using UIKit, right? And basically any buttons, any interactions, anything that you draw to the screen, that's the presentation layer. You'll also include something called view models in the presentation layer. View models are essentially types that you create that hold state for a given view. So if you find that you're writing a SwiftUI view and it has 20 different properties on it, all of them marked at state, right? That starts to feel very unwieldy very fast. Typically, in the Swift development community, people advocate something called MVVM, which is a programming pattern for how to break up these different layers and stuff. Some people can be very prescriptive about it and say, oh, well, if we're using MVVM in one part of the app, we should use it everywhere, and we should use it like this, right? And people get very prescriptive about these kinds of design patterns, very generally speaking. It's more of something that it makes sense when you need it. So if you have a simple view that's got one state property on it, you don't need a view model. Sorry, you just don't. It's completely unnecessary. If you have a very, very important view that has like 20 properties on it that are all state, some of them are bindings, right? All that stuff. You might want a view model, okay? And the view model is kind of a way to wrap all of those properties up into a single type. And then you only need one property of that type on your view. And you can have access to all of that information. It's a code organization thing. It doesn't actually functionally do anything necessarily, but it's helpful. So that's MVVM. You use that when you need it. And we can look at some of that during the live code section that we'll do after this slide deck. So that's the presentation layer. Next up is your logic layer. Some people call this the application layer. Some people call this the business layer or the business logic layer. Basically, this is the part of your app that does work. This is where you are making data transformations, where you are calculating things, running algorithms, you know, any work that your app does that's not being done by a service and that's not being done by the user or by Apple is here in the logic layer, okay? So this is just, if you're adding 1 plus, you know, the user puts in 2 numbers and then you have a special calculator that like, you know, can take in any 2 number types and then add them together, right? That's your logic layer, okay? So that's the logic layer, easy. And then last but not least is your persistence layer. The persistence layer is where you save data, okay? You persist information to a local storage. And then the next time the user opens up their application, the data can be loaded in and it will still be there, right? This is how all app users expect apps to work, right? There needs to be some form of persistence. You need to be able to save things that the user does and creates in some way. Now, a lot of applications that are web-focused will tend to do this purely through the network, purely through a REST API. You'll recall that REST APIs have a number of different types of calls that you can make. They have put, they have delete, right? They have get, of course, but you can use get for anything, right? If the API is built that way, which is, you know, frustrating, but you know, whatever. It is what it is, right? They have CRUD operations, create, I don't remember all the, what's the R? Remake, something? Create something, update, and delete. I can't remember what the R in CRUD is. Does anyone remember what the R in CRUD is? Read, thank you. God, sometimes. It's like I haven't had my coffee yet, but I don't have coffee, so anyway, thank you. Yeah, so create, read, update, delete, right? A lot of people will then basically have a network API act as their persistence layer. Now that only works if your users are always online. That's becoming more and more true in this day and age. However, it's just not guaranteed. You can't always guarantee your users are going to be online. So what do you do in that case? Well, you have to save the information to the device somewhere, somehow. There are a bunch of ways to do that. There's something called user defaults. Often when people are first getting started with Swift and iOS apps, they will save things to user defaults. Please don't save things to user defaults. They are specifically for like user default settings. That's the only thing they're supposed to be for. A lot of people will try and store model data and information in them. Like if I had an app that, I don't know, pulled down every type of pizza that was ever made from an API and I stored it to the local store so that the user can look at it while offline, right? Don't put those in user defaults. Those are not user defaults. Just don't do it. We're not even gonna look at user defaults. I'm not gonna show you them. You don't need them. Don't look at them. If you see someone suggesting them online, that person's an idiot. Don't listen to them, okay? The other things you can do, there's something called Core Data, which is old. It's been around since 2004. It was not actually built to be a persistence layer, hilariously enough, but that's what it became eventually. And that is a sort of database system. There's Swift data, which is built on top of core data, of course, and it's much nicer, and that's what we'll be looking at eventually. And then there's also, you could just save to files, right? You could create your own file type, like .docx, right? Those file extensions, no one registers them anywhere. You can just create them, make them, pick whatever you want. So, yeah, so those are the things you could do. Those are the ways you can persist. Any questions about the different layers of applications and persistence in particular, because that's what we're talking about today. Cool. So, persistence, who dat? It's about carrying stored information across your different app sessions, as we just talked about. It's often accomplished using a REST API. See, I got ahead of myself again. I do this all the time, right? But if we have local persistence, then we can cache the server fetched data locally. We can store it locally, and a call to your local store is typically going to be faster than a call to an endpoint on the network. So that way you can display information to the user very, very quickly if you cache things locally, right? Of note, URL session does actually cache some things for you automatically, but you don't have full control over that. That's something that Apple controls. So, be careful with it. Don't expect it, basically. It's nice when it happens, but don't worry. Don't expect it too much. Try and do your own caching if you can. It lets users work offline, as we said. They can use your application offline. There's nothing more infuriating than opening an application when you are on a plane, or happen to be in a dead zone, or you have very limited bars, and it just spins and spins and spins on the opening screen, and you're just trying to get to the section that is offline. You know that there's a part of your app that should be able to work in an offline state, and it doesn't. It's super infuriating as a user. So you have to make sure that anything that your user could conceivably do without a network connection can be done without a network connection. And the users know. They know. So, be ready for that. And then you can also, of course, merge your modified data with the server later. So this is one of those, if you downloaded a bunch of information, let the user make a bunch of changes, but they're not on the network, so those changes don't get sent to the network, right? Then when your app does come back online, it can send that information up to the server and make the changes up there. All right. So, object relationships, why do we care? In memory, when we have a value or a reference type instance, so you have a class, let's say, that is an animal, right? And that animal class has a bunch of value types on it, right? It has a string that's its name, and it has a number, which is its like size or weight or age or whatever, right? And it also references other animals as animals that it hunted, in the past, things that it's like eaten or whatever, right? Those are basically kind of relationships where one type holds information about another type. And those are typically done through properties. So you'll have a property on your type, and it is of some other type, right? Or in this case, the same type. So like an animal, if it has an array of animals that it's eaten before, that's going to be an array of the animal type, right? And this, in memory, constructs an object graph where different instances of your types, different sections of memory point to other sections of memory. And they say, hey, don't copy what's over there, just look over there. Like that's over there, that's what that is, right? That's what happens when you're using reference types. Obviously, if you're using value types, it's copied. Although in Swift, technically, that's not exactly true. It copies when you need it in Swift. It's like a reference type until you try to do anything where a reference type would change things, and then it becomes a value type. But that's a distinction that you do not need to worry about. So yeah. Yes. So you build a graph, right? Cool. Okay. The graph is handled automatically in memory by automatic reference counting. Thank goodness. We don't have to worry about, we don't have to worry too much about, releasing and retaining and making sure that everything, works right. The only thing we have to worry about with the object graph is strong reference cycles, right? Where one instance refers back to the previous instance, and then it creates a loop that can never be released from memory, right? Beyond that, the graph is properly handled, okay? And we don't have to think about it until now. When we persist to storage, this makes things difficult. How do we actually save this information that's in memory, the shape of it, and how one piece of memory points to another? How do we save that down to the disk? How do we put it onto the user's disk level stuff, right? You could try to just save the reference, right? If we remember, references are essentially pointers. They point to a specific place in memory, right? So I'll actually really quickly just draw this here. So like, I'm gonna go back one. I guess I'm going back many. All right. So you have your memory here, right? And this is your block of memory for one of your types, right? This is your, I don't know, animal, right? Right. This is an animal instance, right? It's a lion, right? This is a string block of memory, right? It's 450 kilograms. I don't know kilograms. What's a kilogram metric? It's like 5 years old, right? And so these are ints, right? And this is a string. Weight should probably be a double, but I'm not going to get into that, right? And then it has its like list of hunted, right? So it's like, this lion has hunted like a gazelle, right? And a hornbill, right? I'm thinking of animals from the intro of Lion King, basically. A zebra, right? Etc., right? These are the things that it's hunted, right? And this is an array of animals, right? Animal instances, which is in and of itself, because it's an array, it's a value type, but what's stored within it are references, okay? So this becomes, right, its own little kind of thing of memory, right? Okay, where these are like memory reference number things, right? Which like they typically look like hex, like there's some hex value, right? Like 8 to 12 character hex value. So this is pointing to some other place in your device's memory that's being used and managed by the app, right? And this is another animal, okay? I should have erased this stuff before I started to draw right next to it. That was a mistake. Here, just get all this. AWS, please. As if. Okay, here we go. So here you've got your next animal, right? And this is your gazelle, right? And it's, I don't know, 200 kilograms. Again, I don't know how much a kilogram is. It was only 2 years old. Oh, that's so sad. And it doesn't hunt animals, so this, hunted animals thing is empty, right? And it's going to have that because it's the same type, right? So its memory shape is going to be the same because it's the same type as that lion instance is, all right? So each instance is a different block in memory, and they point to different other pieces of memory, right? However, the thing to note is that these memory addresses that get used, the ones that actually connect them, those are specific physical places, abstracted of course, but they are specific physical places on your device, okay? Specific physical like registers in your device's memory. And as a result, if you were to just save the reference, right, just in place like it is, just take this whole thing as it is in memory, just shove that into a file, right? Along with the reference here, right? That reference doesn't mean anything the next time the app runs. It's pointing to empty memory. If you were to load every single individual object, ignoring all of the, references until the very, very end, so you load all the other objects into memory and then you try to go through and relink them back up, they're in different places now because the operating system decides where to put your objects and instances based on what is available, right? And your app's memory is boxed into a specific segment. So depending on what other apps are open or being used by the user, you have different memory reference numbers available to you each time your app runs, which means memory references lose meaning when the application stops. That means we can't use memory references to persist our object graph to storage, right? Cool, okay, fine. Well, what if we just save the entire object graph, right? Take the whole thing and just put it into one big object, right? That, doesn't worry about the references, right? It's just, it's its own internal object, and then load that whole thing up, right? The thing is that often when we're persisting, we only need a fraction of the data. The object graph, as it exists in memory, right, is very, very large compared to what you would want to save. Every instance that I've shown here, this memory block for an animal, I've shown you the stuff that we add as programmers. There's about 20 to 50 other things that the operating system adds as a part of its tracking, including its location in memory, right? We don't need all of that. What we need is the data. We just need these pieces of information, right? So if you were to save your object graph from memory, just take the whole thing, just save it into a file, and then just reload that file, you end up with, your save data ends up being very, very, very large, right? Much larger than it would need to be, and it can be prohibitively large, megabytes to gigabytes, which, it's too much, so you don't want that. So, given all of this, how do we handle this? How do we maintain relationships when we are persisting and saving our data to storage? The answer is that we use special IDs. You'll recall that there is a protocol in Swift that we frequently use called identifiable that requires that we define an ID property. It can be a computed one, though, that just references an existing property on our, type. But, basically the idea is, every object, every instance in memory has a unique identifier. And as a result, when we save it and then load it, we know what we're pointing to, right? So we get unique identifiers for each type, for each instance of a type. And then, typically when we're pulling data from a REST API, it also has an ID. And that's because they're using persistence on their side as well. And so their types all have IDs also, typically. Right. So one thing we can do when we're saving data by ID is use Codable and JSON, which we've done before, right? We use that to send our network messages and get data back from the service, right? What if we just take that and put it into a .json file, right? We could do it in a couple of ways. We could use one big file that has all of our instances inside of it. We could have one file per type, where we have an animal type file and a, plant type file. This app example I came up with is terrible. Let's go to pizza. So you have a pizza file, and then you have a toppings file, and then you have like a crust file or something like that. And then every type of pizza instance that you have gets put in the pizza file, and so on and so forth, right? Cool, so that's one option. And then the last option is, of course, one file per instance. So every single instance of every single type that you want to persist gets its own file in somewhere on the disk. Typically, you'll create a folder structure of some sort, right? So this is one way of persisting data. A lot of kind of the newer database systems like Mongo, you know, and I can't remember the other one that I know, but I like the name of. They tend to prefer to use something like this, where they kind of the data gets stored in a what's called a human readable format, right? That's fine, not a problem with that. It depends on your use case what's best to do. Typically, though, if you're not using something like MongoDB, which has been around for a very, very long time and has had a lot of optimization set up for it, each one of these options is going to be very, very slow for a different reason. If you save everything as one big file, right? Everything that you would want saved into one big file, right? Well, let's say that you pull down, I don't know, we'll use the Amiibo app, 600 different Amiibo which exist. And each of those refers to, you know, all the games that can use it, which is hundreds, right? Now you're talking about loading 600 Amiibo into memory all at once, including all of their images and all of the games that use them and all of their images, right? You cannot selectively load only a part of a JSON file because you need to figure out when you're at the end of any given dictionary or array within the JSON, right? So that's just going to fill up. It's going to take a long time to load, and then your memory is going to be huge at the time. You might even get a warning from Apple in your application, hey, stop using so much memory, we're going to shut you down. And if you don't do it in a certain amount of time, they just shut the app down. You just crash. So that has risk. Unless you're using something like MongoDB, which can handle all of that for you, it's not a great idea. One file per type runs into similar issues. Typically, you'll find that when you are working with data store or with data models from the back end, you're going to have a bunch of things, you know, like games and, you know, oh, the type of it and here's all the uses of it and these are the release dates and everything that like on an Amiibo. But one of your types is going to be by far the largest. Like Amiibo, there's 625 of them, right? There's just so many of them that breaking it up into one file per type doesn't really save us anything, okay? It ends up being essentially the same as having one big file. Now, if you have an equivalent amount of types everywhere in all of your types, right, and one isn't going to continue to expand and expand and expand, and they're all going to expand together, then one per file per type works to a point. If the file gets too large, you're still running into the same issue as one big file. And if you have way too many types, you'll run into the same issue as one file per instance. And the issue with one file per instance is that file I/O is very slow. It's very slow. Reading and writing from the disk is slow. It is not as slow as making network calls, right? Well, depends. 5G, I don't know, you know. The world we live in today is very different than when I learned persistence 15 years ago. But memory and RAM and disk is also fast. We have SSDs and NVMe, you know, stuff, which is just blisteringly fast, right? It's almost as fast as, it's faster than memory was 10 years ago, actually. Point being, it's fast now, but it's still way slower than the CPU just doing things, right? And as a result, it can take a long time, and during that time, your user's not using your app, they're waiting for all of the instances to load, right? One at a time. It will take forever, all right? So, now, if you're only gonna have 5 instances ever saved at a time, right? Like, sure, do it, right? But we're not talking about that. We're talking about situations where a user has a calendar app and they have hundreds and hundreds of events in their calendar, possibly thousands, because it repeats, right? So the main thing that we want to wonder is, how do we look this up fast? Because those things are slow. JSON has drawbacks as well. There's things that can't model. The whole file needs to load. Wow, I just did this whole slide without even pulling it up. I'm sorry, guys. Haven't done decks in too long. So one big file, the whole file needs to load. That's the worst choice. One file per type tends to be the best choice, but if some types have massive files, you get the same issue. And then one file per instance, I'd call that the mid or Ohio choice for those of you who use the modern parlance. So that's one file per instance. Each read involves opening an IO stream. Yeah, so opening a brand new stream for IO and reading everything, then closing the stream and then doing it again, that just takes forever. And by forever, I mean like 200 milliseconds instead of 20, right? Which is still 10 times more, but you know. Okay, so how do we do this quickly? How do we save the data and then read it quickly? We can use something called a relational database. A relational database they've been around since the 60s. They have been writing things to very, very, very slow magnetic tape disks for a very, very, very long time. This is a model for data persistence that has existed since before any of us were born, and it will continue to exist after we perish, most likely, because it is currently still one of your most efficient ways of storing data, assuming you do it correctly. It has the structure of how relational databases work are very well known and very well understood because they've been around for so long. The way that you optimize them, the way that you read from them quickly, write to them quickly, the way that you query them quickly is just, it's been looked at by people who are so much smarter than me, so many years. And they've been working this problem for a very, very long time. And the structure and best practices of relational databases are very well understood. They have extremely fast queries. Also, search is what a normal person would use, but because we're programmers, we call them queries because we like to be weird, right? And so they're very fast at doing queries if you set your database up correctly, right? And that's kind of the trick. You need to make sure you set it up right. They have a very specific way that they save type references, type instances, and we'll take a look at that shortly. And this very specific way of saving type instances is it's how it's been done in relational data stores for a very long time. And other than newer things like MongoDB, which use JSON to back them, it hasn't really changed. And everyone got really excited when Mongo came out and all these other JSON-based databases and stuff like 10 years ago. And at the end of the day, people still use relational databases when they actually want to be fast. And again, anytime you're reading to the disk and writing from the disk, or writing to and reading from the disk, it is always going to be slow, quote unquote, based on the CPU, right? If you're comparing it to how quickly the CPU can do something. But this has been getting optimized for decades. The most well-known example of relational databases is SQL. That's the correct way of saying it. But everyone I know, me and my homies, call it SQL, okay? And I will continue to call it SQL because it's more fun, even though it's not correct. But everyone I know calls it SQL. And if you say SQL, people know what you mean. If someone's like, actually, it's called SQL, tell them to touch grass. So, SQL databases. Let's talk about those a little bit. In SQL, things are stored as tables with columns and records. That's it. It's very, very simple, okay? So, tables represent entities, okay? These are concepts, model objects. You might recognize them from Swiftland as types, okay? Types are tables, and tables are types, right? It is a blueprint for how to store data and information about something. However, instead of doing it in memory, like we do, because we're cool, it does it to a local storage table because it's slow and boring, right? But, we need it. So we try not to say insulting things to its face too frequently. Just every once in a while, I'll throw some shade at databases, but primarily, they're helpful. They're just annoying. Okay. So columns represent attributes. Now, shoot. I did not mean to have it say attributes. Don't worry too much about, ignore the attributes thing, because I don't believe that's technically correct with SQL. I was like, I'm just gonna put something here and I'll double check it later, but I don't remember the actual technical term, so please ignore attributes. I'm gonna go edit that with a strike through before I post this slide deck. Or I might update it to the correct term. I don't remember what it is off the top of my head. But in the terms of types, you can consider these to be properties. Okay, columns are the different kinds of data for that particular entity. Okay, so a pizza will have a name, right? If we're defining pizza as something on a menu, right? A pizza will have a name, it will have a crust, and it will have toppings, a list of toppings on it, right? And you can use this information to create a menu for a pizza restaurant, right? Rows represent records. Records are instances. So again, in memory, if we have a reference type, like a class, and there is an instance of it in memory. So we have a bunch of different pizza type, right, instances all loaded into memory. We're showing them in a list. They're all very cool, right? It's the same thing here. We have a row for each instance, okay? Now in these rows, they are all required to have an ID. And that ID is often handled by whatever framework you're using to access the database, so you don't have to worry about it too much. But it's good to know that it's there, okay? Because that's going to talk about how we actually connect and build the object graph using tables, right? Okay. So all of this, you know, what is a table? What is a column? What is a row? All of that gets defined by a schema. A schema is the definition for all of this information. It says, oh, okay, we have a pizza entity, and the pizza entity has a bunch of, you know, it has a name column and a crust column and a toppings column, right? And I guess this schema doesn't actually define the rows. The rows are defined when you write into the database, right? Right, the columns and the tables are. So that's the shape of the information. Okay, any questions about SQL, tables, columns, records, oh my, databases, JSON, MongoDB, any of this stuff we've talked about before we start talking about relationships, while I grab a quick drink of water because I'm parched.
Do you use it?
It's relevant. I'm building to a big reveal. Yeah. So, yeah. Okay. This is databases. I'm telling you all this just in case you don't know. You might already know some of this stuff. Great, awesome. If you didn't know this stuff, well, now you do. And it's important to know because, well, you'll see. So, last but not least, let's talk about relationships. Relationships exist between entities, right? And we know this because we use reference types all the time. And we have properties that point to other references. And we have arrays and dictionaries, and they're all pointing to each other all over the place willy-nilly, and we don't define it. We don't say, oh yeah, well this relationship is like this, and this one is like this. With databases, and specifically SQL and any SQL-derived database, you do define what that relationship is. You say more than just, oh, I have a reference to an array of this, or whatever. You put metadata around it, and that metadata allows the database to do very, very, very fast queries when you're trying to find information, right? So, it's complicated. Relationships come in three primary forms with a little bit of seasoning on top. There are one-to-one relationships. One-to-one relationships are relationships where you only have a reference to a single other instance on your instance. So there's only a one directional pointer, right? It just points and that's it. And that one might point back, right? And you know, whatever, but like there's only one of each at any given time. That's one-to-one, okay? Next, there's one-to-many. And I've also shown, you know, here in the commas, the many ways that people talk about these, and I've missed a bunch because I didn't want to make the text tiny to fit them all. But there's a lot of ways of writing these three concepts, okay? So there's one-to-one, one-to-many. One-to-many is your most common type of relationship that you're ever going to run into. In a one-to-many relationship, there is one row or instance or record, whatever you want to call it, that refers to, it has a column, right, a property, that refers to a number of other records in some other table, right? Or it has a bunch of instance information about another type. Another way of putting it, okay? Same concept. So you have a list, basically, of a bunch of different things as a possibility, then, or that are stored, then you have a one-to-many relationship. One-to-many relationships, like one-to-one relationships, it could be set up in a way where, say, the pizza has a reference to the crust, and the crust does not have a reference back to the pizza, right? Very common way to set up one-to-one. Also very common way to set up one-to-many. Very frequently a one-to-many relationship will be set up such that the pizza has a reference to a bunch of, pizza bases, right? Such as, small, medium, large, vegan, gluten-free, whatever, right? All the different kind of options you would want for the base of your pizza, the thing that you're gonna build everything upon, right? That's your pizza base. So in a menu of pizzas, one type of pizza can have a bunch of different options, right? You could be a small, medium or large, but you might want to limit that for some types of pizza, right? Point being, you can set this up so that base knows which types of pizza use it. So if you have a base that is intended to, its instance is intended to represent a vegan option, right? Your users might want to be able to search on the concept of a vegan pizza. In order to do that, the vegan base instance needs to know which pizza instances use it in order to do this quickly. You could just go through every single pizza instance and try and find which ones have vegan in their list, right? That is absolutely an option, and it's typically what we'll do in memory, right? But in databases, because reading in databases is so slow, we prefer to, if we need to make those queries, set up a reverse or bidirectional relationship between the two different tables, okay? So your base is going to know what pizzas have it, and your pizza is going to know what bases are available to it. Cool. Last but not least is the fun and difficult and painful many-to-many relationship. In the many-to-many relationship, you're going to have basically a bunch of things. I just realized, I don't know why I used base as an example here, because that's actually, pretty sure that's a many-to-many relationship. One base can have many pizzas in base. Right, oh, I see. Okay, yeah, sure. Sorry. So this would be unidirectional, not bidirectional. Ignore that arrow on the middle one. Many-to-many relationships. So again, let's say you want to be able to search by topping. What pizzas have pepperoni on them, right? Then topping would have a list of pizzas that have pepperoni on them, right? A bidirectional one-to-many relationship, each base would have a single pizza that it refers to. So it would point back to a single pizza, right? Which obviously that doesn't work here. Apologies. My example in the middle sucks. It's what you get for writing lecture slides at 11 p.m. When you're, you woke up at 6 a.m. So a topping is going to be more like what we described, where pizza's going to have a list of toppings, and toppings are going to have a list of pizzas that they are on.